Welcome to AI Paper Podcasts. Today we're diving into a paper tackling something huge, building AI world models. These are, the really ambitious systems meant to truly understand and simulate our physical world, not just recognize objects in photos.
Right, it's about understanding the physics, the motion, the cause and effect.
Exactly. Think AI that predicts how things move, figures out why things happen, and even generates content that, actually follows the laws of physics.
It's a big goal.
Huge. But the central challenge, the real bottleneck, has always been the data. Like, what if the stuff we're training these AIs on just isn't dynamic enough or diverse enough?
And that's precisely where this paper and the OmniWorld Data Set comes in. It's presented as a real game changer.
Okay, tell us about it.
Well, OmniWorld is this massive data set, multi-domain, multimodal, specifically engineered to basically smash through that data bottleneck we just mentioned.
Massive are we talking?
Over 300 million frames total. And get this, 18 million of those are from a custom-built synthetic part called OmniWorld Game.
Wow.
And the key is its breadth. It pulls data from game simulators,
Right.
which gives you amazing control and ground truth.
Right.
But also from real-world robots, footage of human activities, even large data sets scraped from the internet.
So a real mix.
A huge mix. And it's incredibly rich in modalities. So not just the video, the RGB frames, but also crucial geometric stuff. Depth maps, so how far away things are. Camera poses exactly where the camera's looking from.
Super important for 3D.
Essential. Plus optical flow for pixel-level motion, detailed text captions describing the scene, and even foreground masks to separate moving objects from the background.
Okay, so this isn't just another data set dump. It sounds like it has a specific purpose, or maybe two.
Exactly. It's positioned as this dual-purpose powerhouse. First, it's a really challenging benchmark. It actually exposes some surprising limitations in current state-of-the-art models.
Pushing them hard.
Pushing them really hard. But second, it's also a powerful training resource. The paper shows that fine-tuning models on OmniWorld significantly boost their performance.
Interesting. So it's like a tough exam and the study guide.
That's a great way to put it. It's a reality check and a masterclass for these AI models.
Okay, let's really unpack this. How is OmniWorld actually helping us build AI that gets the physical world, moving beyond just labeling things to really understanding dynamics?
Right.
So let's start with that big vision again, the world models. We said it's about simulating dynamic environments.
Predicting object motion.
Inferring causality, generating content that looks physically plausible.
Yeah, it's a universe away from just recognizing, say, a cat in a static image. It's about understanding the physics and the interactions within a scene over time.
But this vision, as exciting as it is, keeps hitting a wall, right? Because of the data limitations you mentioned earlier.
Exactly. The existing data often just doesn't cut it. Take benchmarks for a 3D geometric understanding. Models trying to grasp the 3D structure of a scene.
Okay.
Many standard ones, like Cintel, for instance, have videos that average only about 50 frames. That's like, what, less than 2 seconds?
Way too short.
Far too short to evaluate long-term robustness. Can the model keep a stable understanding as things move and change over, say, 10 or 15 seconds? These short clips just don't test that. Temporal consistency is a huge issue.
And it's not just the length, is it? It's the variety.
Precisely. The motion and scene diversity are often lacking. You get data sets focused on narrow scenarios. Like, BON is mostly indoor human motion. KPI is very specific outdoor street scenes, mainly driving.
So they miss complex dynamic environments.
Totally. Bustling kitchens, complex robot interactions, crowded outdoor spaces with unpredictable movement.
Right.
And then there's the lack of those geometric modalities we talked about.
The depth maps, camera poses.
Right. You have tons of image text or video text data sets out there now, which is great for some things. But they often miss depth, pose, optical flow, the stuff you need for true 3D spatial understanding.
It feels like trying to learn physics just by reading descriptions.
Kind of, yeah. And even in video generation, datasets like Real Estate 10K, while large, mostly feature static scenes, smooth camera pans over landscapes or architecture.
Not exactly representative of real-world action.
Not at all. It's a far cry from the chaotic, dynamic interactions you see every day.
So putting it all together, we have these incredibly sophisticated models, but they're being trained on data that's too short, too simple, too static, and often missing the crucial 3D information.
That's the core problem they identified.
It sounds like they're trying to, learn to run a marathon by just jogging on a treadmill for a few seconds at a time.
That's a perfect analogy. They're starved of the complex, dynamic, real-world nutrition they need to actually develop robust world understanding.
Okay, so enter OmniWorld as the solution. You said it has two main parts.
That's right. It's built from two main components. First, there's OmniWorld Game, which is their massive self-collected synthetic data set.
The one with 18 million frames.
Yep. Over 96,000 distinct clips, adding up to more than 214 hours of video. And it's high-quality 720p RGB images.
And crucially, it has those perfect annotations because it's synthetic.
Exactly. You get dense ground truth depth maps, perfectly accurate depth info straight from the game engine, precise camera poses, plus rich annotations for text, optical flow, and foreground masks.
How does it stack up against other synthetic data sets?
Well, according to their comparisons, OmniWorld Game is pretty much unparalleled in its scale, and importantly, the diversity of data modalities it offers simultaneously.
Okay, that's the synthetic part. What's the other component?
The other part is the integration of several high-quality public data sets from diverse real-world domains.
So combining the best of synthetic control with real-world messiness.
Precisely. That multi-domain aspect is key. It's not just piling on more data, it's about getting different kinds of data, different experiences for the AI.
Makes sense. What are these domains?
They structure around 4 key domains. First is the simulator domain, which is primarily that OmniWorld Game data set we just discussed.
Right, high-precision synthetic data.
Yeah, temporally consistent, multimodal, directly from game engines. They show examples like, a detailed kitchen scene, someone grasping a bowl. They use tools like Reshade for depth extraction and OBS for synchronized video capture. This gives them not just accuracy, but also diverse scenarios, wilderness, cities, day, night.
Okay, domain 1, simulator. What's next?
Second is the robot domain. Here, they integrated public data sets like Agibot, Deoroid, RH20T. This gives you crucial data on robots actually interacting with environments, manipulating objects, navigating.
Essential for robotics applications, obviously.
Absolutely. Third is the human domain. And this is actually the largest slice of the OmniWorld pie. It includes data sets you might know, like HOI 4D, Epic Kitchens, Ego Exo 4D, Hollow Assist.
Lots of human activity data.
A ton of it, capturing all sorts of activities, crucially from both first-person egocentric views and third-person exocentric views. So you see the action from the actor's perspective and an observer's.
Like seeing someone grab a bottle from their own eyes and from across the room.
Exactly. And finally, fourth is the internet domain. This uses large-scale public data sets like City Walk, basically, realistic street view videos, often with added camera pose data, grounding things in real-world urban dynamics.
Okay, simulator, robot, human, internet. That's a really broad mix.
Yeah.
But you mentioned the annotations earlier. That seems like a huge part of the value here.
It absolutely is. The level of detail in the annotations is, well, pretty staggering. It's a masterclass in data engineering, frankly.
Let's break that down. How did they get, say, the depth maps for everything, ground truth for the game, you said?
Right, ground truth for OmniWorld Game. For the public data sets where depth can be noisy or missing, they use some clever techniques. They mentioned prior depth anything to optimize existing noisy data, and foundation stereo to process input from stereo cameras. So they're really working to get high fidelity depth across the board.
Okay, what about those foreground masks, separating the main actors?
Crucial for understanding interaction. They automated this with pipelines combining things like RoboEngine and SAM2 for robots, and grounding Dino plus SAM for game characters. The goal was precise, temporally consistent masks, knowing exactly what's moving and interacting.
And camera poses. You said those are tricky.
Notoriously tricky in dynamic videos. Motion blur, occlusions, fast movements. It's hard. They developed this robust two-stage automated pipeline.
How does it work?
Well, it cleverly uses those foreground masks first to sort of ignore the moving stuff and focus on the static background parts, which are easier to track.
Smart.
Then they use tools like VGGT or Droid Caleb for a rough, coarse estimate of the camera pose. Then they refine it using dense point tracking. They mentioned CoTracker 3 and a technique called bundle adjustment.
Bundle adjustment that optimizes everything together.
Exactly. It optimizes the 3D points, the camera positions, everything simultaneously to get the most accurate result possible. It's computationally intensive, but gives great results.
Okay, depth, masks, poses. What about the text captions?
Also really impressive. Generated semi-automatically using a large vision language model. Qwen2 VL72B Instruct, apparently. They use specific prompts tailored to the domain and viewpoint.
Give me an example.
Like, a man in a suit walks along tram tracks in an urban setting, and it goes on, describing the scene in detail. These captions are typically 150 to 250 tokens long.
That's much richer than typical short captions.
Way richer. More descriptive than many existing video text datasets. And finally, Optical Flow, the pixel-level motion.
Right.
For that, they use DP Flow, a method that can handle different video resolutions directly, capturing that fine-grained motion accurately across the varied data sources.
So just to recap the scale again, over 600,000 video sequences, 300 million frames, high resolution. But the internal structure of OmniWorld Game itself sounds important too.
It really is. It's not just random game footage. They specifically composed it to cover varied scene types, outdoor, indoor, natural, urban, different camera views, first person, third person, even different historical eras, ancient, modern, futuristic, and a diverse range of dominant objects, terrain, buildings, vehicles, characters. It's structured for complexity, designed to teach AI general world understanding, not just one specific scenario.
It's like building a miniature, diverse digital universe specifically for AI training.
That's a good way to think about it. The breadth and depth are meant to challenge AI systems and force them to generalize.
Which brings us neatly to OmniWorld as a benchmark. This is where we see if current models can actually handle this diverse, dynamic universe.
Precisely. This is where the rubber meets the road. OmniWorld Game, in particular, serves as a super challenging benchmark for two key tasks. First, 3D geometric prediction.
Understanding the 3D structure.
Right. And as we discussed, existing benchmarks are often too easy, short sequences, limited motion. OmniWorld Game just cranks up the difficulty. Longer sequences up to 16 seconds, 384 frames, complex, diverse motion, extreme scenarios, high resolution.
So how did the state-of-the-art models do?
Well, they struggled. Top models like GUST3R, MASC3R, Moj2, really strong contenders, found it tough. Yeah, Moji2 did relatively best for monocular depth, so guessing depth from one camera view. But the paper still says there's significant room for improvement.
And for video depth, using multiple frames.
There, VGGT performed better, but still showed noticeable artifacts. The big problem was maintaining temporal consistency. The depth map would kind of flicker or jump around inconsistently between frames, especially in dynamic areas.
You can really see that instability in the 3D point cloud visualizations they show. Some models just produce noise, while others, like VGGT, are more coherent, but still miss details or have weird distortions.
Exactly. It highlights this really important question. How robust are our current models when you throw truly complex, dynamic, real-world-like scenarios at them?
The answer seems to be not as robust as we might think.
That's the takeaway. They lack the resilience for these continuous, complex scenes. Okay, second benchmark task. Camera-controlled video generation.
Generating video along a specific camera path.
Yep. Again, existing benchmarks often use simple static scenes and smooth camera moves. OmniWorld Game throws dynamic content, diverse scenes, complex camera paths, and multimodal inputs at the models.
And the results? Similar story.
Pretty similar. Top models like AC3D, MotionTrell, CamTrol, CAMI2V showed, well, significant limitations. AC3D, for instance, could generate video that made sense semantically.
Okay.
But it often failed to actually follow the requested camera trajectory accurately. And the motion of things like people in the scene was minimal.
What about others, like CamTrol?
CamTrol did better on aligning with the camera path, but the paper notes issues like blurry moving characters and just generally poor video quality. It seems precisely controlling a complex camera move while rendering dynamic objects consistently is still a major hurdle.
So across both geometry and generation, OmniWorld really exposes this gap between current capabilities and the demands of truly dynamic scenes. If you had to pick one core challenge it highlights.
I'd say it's the twin challenge of temporal consistency and fine-grained physical control. Models can generate a decent single frame, maybe even a short, smooth sequence.
Right.
But maintaining a stable, physically plausible, and accurately controlled representation over time in a complex dynamic scene. That's where things often break down. OmniWorld really puts a spotlight on that brittleness.
And overcoming that seems critical for, well, almost any advanced AI application involving the real world. Robotics, VR, autonomous systems.
Absolutely. You need that consistent, controllable understanding of dynamics. But okay, OmniWorld isn't just about pointing out flaws, it's also proposed as a solution. A powerful teacher.
Right, the training resource aspect. How effective is it?
The paper shows really consistently positive results. They took several of these state-of-the-art models and simply fine-tuned them on OmniWorld data.
Just continued training them, but using OmniWorld.
Exactly. And the performance boost was often significant.
Give us some examples. What happened with 3D geometric prediction?
Okay, so take DIST3R. The fine-tuned version, which they call DUST3R, showed significant improvements over the original on standard public benchmarks, Cintel Bond, KT-I, NYU V2. This was for both monocular and video depth estimation.
So training on OmniWorld helped it perform better even on other datasets.
Yes, significantly better. In some cases, DUST3R even outperformed other models that had been heavily tuned specifically for those benchmarks. They saw similar gains with another model, CUT3R.
What about camera pose estimation?
Same story. Fine-tuned models like CT3R and ReLock3 showed much better accuracy in estimating relative camera poses compared to their original versions.
That's pretty compelling evidence for generalization improvement. What about the video generation side?
Similar results there too. The fine-tuned AC3D model showed substantial improvements on both the standard real estate 10K benchmark and on the challenging OmniWorld Game benchmark itself.
How did it improve?
The generated videos followed the desired camera paths much more closely. And crucially, they maintained better temporal consistency for moving objects. The paper has side-by-side comparisons where, say, AC3D generates a character riding a horse along a path, and the camera movement and the horse's animation are just much more stable and accurate than the original AC3D.
That really drives home the point, doesn't it, that dynamic data is key.
It couldn't be clearer. What's fascinating is how directly it shows that feeding models this dynamic multimodal data is critical for improving not just specific tasks like camera control, but their broader world modeling capabilities. It's the type of data capturing real-world dynamism and physics that makes the difference.
So OmniWorld really validates itself here. It's not just a tough benchmark, it's genuinely valuable as a large-scale training resource. It demonstrably enhances the generalization and robustness of these foundational AI models.
Absolutely. It's pushing the whole field forward by providing both a challenge and the means to overcome it.
Okay, let's wrap this up. The core message seems clear. OmniWorld is tackling a fundamental data problem for AI world models head-on.
By providing this unprecedented scale and diversity, multimodal, multi-domain data.
And its dual role is key. It's a demanding benchmark revealing where current models fall short.
Especially on temporal consistency and dynamic control.
And it's also a powerful training resource that demonstrably boosts their performance and generalization.
Exactly. It's both the test and the textbook.
And looking forward, the implications seem huge. Datasets like OmniWorld are likely to seriously accelerate the development of more general, more robust AI. Models that can really understand, simulate, and maybe even interact with our complex physical world.
We're talking AI that gets physics, understands complex instructions in dynamic scenes, generates realistic, controllable scenarios. It opens up a lot of possibilities.
It really does.
But it also leaves us with a really interesting, maybe profound question, doesn't it? As these AI models get ever more sophisticated, how much more nuanced, how much more real does our synthetic data need to become? How closely do we need to simulate reality in the digital world to unlock that next generation of truly intelligent systems? It feels like a continuous chase.
That's a great point to ponder. How real is real enough for AI? Fascinating stuff. Well, thank you for breaking down OmniWorld for us. It's clearly a landmark contribution. And thank you all for joining us on AI Paper Podcast. We hope you'll keep exploring the frontiers of AI with us.